Hi, everybody, and welcome again. Welcome to Smith Mountain Lake. I wanted to create a video that talks about I'd say one of the biggest challenges that I had that I recall when I was a student. So even after all these years, one of the things that I faced as I was getting ready to take test one was keeping straight in my mind what fundamentals apply to a closed system and what fundamentals apply to an open system. And so this is what this video is going to be about. Now, this is not a preparation for taking test one, because there's other details to get ready. And I try to cover that in a different video. So of course, I recommend you have a look at that video too. But it's my hope that this video will help you keep straight and also simplify the fundamentals that you're learning in your head. So here we go. Okay, and so I call this open system versus closed system. And I'm trying to give you a few tricks of the trade, things that have helped me out to succeed as a student, and then be well positioned to succeed as a practicing engineer. Okay, so here's the objectives. Quickly review what's a closed system versus what's an open system. How are these different and how are they similar? Then we're going to go make a comparison with the continuity equation, conservation of mass. How are these different and how are they similar for closed and open systems? And then finally, we're going to state the first law of thermodynamics for both closed and open systems. Compare those. How are they different? How are they similar? And so what I want to encourage you to do is try to use your eyes and your head to simplify what you need to commit to memory. So it is not going to be enough to simply prepare a formula sheet for success in this class. Formula sheets can help you get through quizzes and tests, but they're not going to help you excel. Just to repeat then, there are certainly things you're going to want to commit to memory, and open system, closed system, the continuity equation, and the first law of thermodynamics definitely fall into that basket of things that you must commit to memory. All right, well, let's start with a sketch. Any problem you have, you always want to start with a sketch. So I've tried to depict a generic closed system and a generic open system. Let's look at the closed system first. How many homework problems have you had now where you had a piston and cylinder and you drew a control surface to depict where the mass is contained? And this piston and cylinder tends to be a pretty good representation of a generic closed system. Remember that a closed system can be a rigid container. And so, of course, you could see how this piston and cylinder could become a rigid container if you pin down the piston. All right. So mass is fixed within the control surface, and there's the example. And so recognize here in my little start with a sketch, I've depicted state one where the piston is down here, and I've depicted state two where the piston is up there, just to try to give you an example of sketches that we draw for closed systems. Now let's jump over to an open system. So open systems can look like all kinds of different things. They can look like pumps, turbines, compressors, nozzles, heat exchangers, all kind of different looking things. So I've had to draw a cloud. And within that cloud, I've drawn a control surface with that dashed line. Here's the way you can tell that's an open system. Mass is flowing into and out of the control surface. So for this example, I've got one mass flowing in at state one, kind of like a pipe going in, and I've got one mass flow coming out at state two. Okay, what else have I shown on both closed and open systems? Open system, I'm showing W dot out. That is output power. That's the rate at which we're doing work. I'm showing Q dot in. That's the rate of heat transfer going in. So this is a generic open system. I think you've got it. Let's jump back because I forgot to say something about the closed system. Typically, we're studying a process that goes from state one to state two. And during that process, some work is done by the closed system, W out, and some heat is added to the system, Q in. And so I do want you to recognize with your eyes the difference between W out and W dot out. This is output work in kilojoules. This is output power in kilowatts. A watt is a joule per second. And then you could do the same thing. This is the heat transfer in kilojoules. Okay. This is the rate of heat transfer into the open system, kilowatts or kilojoules per second. Okay. So I think you got it. But man, this was like step one. Once you've drawn your sketch, step one is write down on your paper, open system or closed system. I harped on this when we were just working on closed systems, and you might have thought, why is this guy doing this? Well, the reason now is, as engineers, you're now faced with reading a problem quickly and having to decide, is this an open system or closed system? And amazingly, it'll come to you quickly the more practice you get. All right. For this presentation, we're going to keep it simple. I'm not going to throw differential equations at you. I'm not going to throw, just any generic open system at you. We're going to restrict our examples for this presentation. Okay, a closed system for this presentation, undergoing some process from state 1 to state 2, and that's it. For our open system example, we're going to say our open system is operating at steady state, steady flow conditions. Things don't depend on time, but they're operating at a constant rate. Whatever's happening at breakfast time is exactly the same thing as what's happening for the open system at lunchtime. Okay. And we're only going to have one inlet and one outlet just to keep it simple here. So the inlet state, we're going to call it state 1. And the outlet state, we're going to call it state 2. So do recognize, of course, there's lots of additional situations, but our purpose for this presentation is comparing and contrasting how you attack an open system and how you attack a closed system problem. Okay. How are open and closed systems similar and different? They're similar. Both of these use some type of control volume, that dashed line, to designate the system boundary where you show in your sketch. Both are used to describe some process. Okay. Both can involve work and heat transfer, or the rate at which work is done and the rate at which heat is transferred. Okay. Both of those occur at the system boundary. That's what is similar. Those two energy transfer phenomena, heat and work, occur across the system boundary. Those are the similarities. What makes open and closed systems different? Okay. Closed system, mass is fixed. Different. Mass flows into and out of an open system. That's the way to observe you got an open system. Okay. Open systems involve rates. Mass flow, m dot. Heat transfer rate, q dot. And power, W dot. Closed systems, usually, there have been a few exceptions and little specially worded problems, but in general, closed systems involve energy change, delta U, heat transfer, Q in, or work out, W out. And the units of those would be things like joules, or foot-pounds force, or BTUs. Okay. Let's move along to the continuity equation, also called conservation of mass. How are they the same? How are they different? So we'll write down the continuity equation for a closed system, all right? Pretty easy. You should have this in your head. Forget the formula sheet stuff. M1 equals M2. The mass at state 1 is exactly the same mass as what's in state 2. And in problem solving, we call that M, the mass. Mass of the closed system is constant for the process from start to end. Open system, a little more complex, but similar. Okay, we've identified that we've got an open system. We see flow in and out. We say, for this example, we're going to have steady state, steady flow conditions things are coming in steadily, things are leaving steadily. The state at 1 is the same at all time, and the state at state 2 is the same at all time. Okay, so here's what we say. We say m dot 1 equals m dot 2. That's the continuity equation. The mass flow rates must balance exactly because the open system is not getting fatter or skinnier. It's staying with the same mass. Okay, and so for problem solving, we call that m dot, the mass flow rate, m dot. Okay. Now, we take a little side trip and talk about open systems only because in nearly all of your problems, all of your homework problems, quiz problems, and test problems, you're going to be, unless you're given the mass flow rate, m dot, you got to figure out how to find the mass flow rate. And so many students overlook this handy dandy fundamental in your book. M dot equals rho A V. Or in other words, for our steady state, steady flow problem, m dot is equal to rho 1 A1 V1. And that exactly equals rho 2 A2 V2. Let's see, rho, density, kilograms per cubic meter. Area, square meters. Velocity, meters per second. Okay. Or, okay, if you say, well, I didn't see that in the textbook. You're making up something. Well, no, on the textbook, maybe you saw m dot equals A1 V1 divided by little v1, which is identically equal to A2 V2 divided by little v2. Well, why are we writing both of these down? You should know this in your head. You should know in your head that density is the reciprocal of specific volume. So these two statements of how to find mass flow rate are identical. Okay, should have that in your head. Okay, key continuity equation differences. So notice here, I've tried another simple slide. The mass is fixed for a closed system. Recognize M1 and M2. The subscript 1 represents the starting state, and state 2 represents the ending state. And this mass M is going to have units, kilograms or pound mass. Let's look at the difference. Looks a little similar, but definitely different for an open system with steady state, steady flow, one inlet, one outlet. M dot equals M dot 1 equals M dot 2. Recognize the dots. That's different. Okay. Recognize the subscript 1 represents the state of what's going into the control volume. The state 2 represents the state of what's going out of the control volume. The process occurs at the open system boundary. Okay, so there we go. The dots over the M's reflect the rate of mass flow. So our units are going to be kilograms per second or pounds per second for M dot. Looks similar, but big difference. Now, looking ahead towards what you're writing down on your pencil and paper. If you have an open system, don't write down just M. That's not an adequate solution approach. Many students do that. Open system, you need to be writing down M dots. Now moving on to the first law, even more powerful. Okay, we've got one slide that's for only closed system. Here's my sketch. Looks familiar. Closed system, fixed mass. You need to commit to memory this statement of the first law. Q in minus the work out equals changes in energy of the closed system, delta U plus delta KE plus delta PE plus delta other energies that we don't work much with, but by golly, we do work an awful lot with the changes in these three energies, don't we? Okay. You got to commit that to memory. So of course you'll put this on a formula sheet, but this has got to be in your memory banks. The next statements are identical to one another. So as you're thinking, as you're reviewing things in your mind, can you get from one step to the next, to the next, to the next? Delta U is capital U2 minus capital U1, the change in internal energy. Next step, okay, Q in minus W out is the mass times little U2 minus little U1. That's specific internal energy. That's the mass of the closed system. Kinetic energy change. In your mind, can you go from delta KE to this expression, 1/2 mass of the mass of the closed system times V2 squared minus V1 squared, okay, plus change in potential energy. But this, you got to know how to get this right out of the top of your head. Another thing that we do an awful lot in many of the homework problems you've done so far is for this closed system, you divide both sides by M. Divide both sides by the mass to get little q in minus little w out. That's kilojoules per kilogram. Up here, capital Q in, kilojoules. Little q in, kilojoules per kilogram of the closed system mass, equals all these things in little units. Change in internal energy, change in kinetic energy, change in potential energy, and you see the mass has been divided out. Let's compare that. So you got to have this in your mind. Formula sheet, okay. Got to have this, at least this top fundamental in your mind, closed system. Let's move on to open system, first law of thermodynamics. All right, here's my sketch. For this example, one inlet and one outlet, steady state, steady flow. Okay, here's the first law. It's conservation of energy. Q dot in minus W dot out equals M dot, the mass flow, times a bunch of bracket terms, H2 minus H1, plus V2 squared over 2 minus V1 squared over 2, plus G times vertical position Z2 minus vertical position Z1. Based from a datum, how high 0.2 is and how high 0.1 is. That's potential energy. Okay, you got to commit this to memory. You got to get this in your memory bank. Okay, so wait a minute. Hard to memorize this. Well, let's see. Q dot in minus W dot out. That should be pretty easy. M dot times a big bracket bunch of stuff. That's pretty easy. Bracket stuff. Well, enthalpy change. That is internal energy with flow work incorporated into it that you would have covered in your class. Enthalpy change plus kinetic energy change plus potential energy change. Okay. And then for homework problem solving, particularly in this textbook, you can divide both sides by M dot. You don't need to memorize this. Look, you got this memorized. You got this committed to memory. You can quickly determine this, this expression. So, and I see that in my slide, I need to change E and I to 2 and 1. So that's something I missed when I was proofreading. All right. Let's compare. Now we got a slide where we're comparing a closed system first law to an open system first law. And well, let's look at it. Let's just visually look at this slide without reading off the equation. Look at the left-hand side. The left-hand side is a bunch of boundary phenomena, energy transfer that occurs at the system boundary. Closed system, Q in minus W out. Left-hand side for open system, Q dot in minus W dot out. Look at that similarity. Okay. Right-hand side, energy changes. I've got mass times U2 minus U1. That's internal energy change, isn't it? Let's go down here. M dot times enthalpy change. That's similar. It's similar but different. That's why I've colored these two blocks yellow. Next block of things. Kinetic energy change. Look how similar. I've got 1/2 M V2 squared minus V1 squared. And down here in the open system, I've got 1/2 V2 squared minus V1 squared. I didn't pull the half out. You can see that. Kinetic, look how similar, but not identical, kinetic energy change is. And similarly, look how similar the potential energy change term is. And so it is my hope that the light bulb goes on and you can see the similarities and slight differences between closed system and open system first law. That's kind of like my big reveal. And if you can get this into your head, you're going to benefit yourself so much in problem solving when time is critical, when you don't have quite so much time to think about what I've got, to go back to the book, look for an example problem. You don't have that luxury. Okay, so things that are different. Let's look at first law differences for a closed system. Closed system, we're looking at process 1 to 2, not inlets and outlets. Units of all these computational blocks, all of them have got to be consistent in units, and the units will either be kilojoules or BTUs or foot-pounds force. All those terms must have those units. They've got to be consistent in units. Open system, you're dealing with rates. You see these dots all over your heat transfer and mass flow terms, rates. And so the units are going to be kilowatts, BTUs per second, horsepower. Those terms will be consistent with those units. Okay. Catch up a little bit on textbook practices. So the textbook homework and particularly a lot of homework problems ask for little w out or little q in for both closed and open systems. And so let's see what that means, just so you'll have this a little bit in your head. For a closed system, you're dividing the heat transfer and the work by the mass of the system, little w out. Okay. On the open system problems, you're coming up with the same variable name, W out and Q in, but what you've got is output power divided by mass flow rate, and you have heat transfer rate divided by mass flow rate. And so these variables look visually identical, but they are different, okay? What's similar? They're both expressed on a per mass basis, okay? The units will be kilojoules per kilogram or BTUs per pound mass. What's different? Closed system is per kilogram of system mass, and open system is per mass flow rate, rate per mass flow rate. So another very subtle difference. I'm just trying to encourage you to get this stuff up in your head rather than depending on a formula sheet for a crutch. And that's exactly what a formula sheet is. It is a crutch. Okay, let's recap on what we've covered. Going into test 1, it's going to be a little different than homeworks because it's not going to be the problems on a test are not going to be identified. This is from chapter 4. This is from chapter 3. You got to read the words and you decide, is it an open system or a closed system? Many students go into tests not having that skill. That's not you. That's somebody else. Continuity equation. You should have the continuity equation statement both for closed and open system in your head. First law of thermodynamics. You should have the first law of thermodynamics, the conservation of energy statement in your head for a closed system and for an open system, at least for one inlet and one outlet, steady state, steady flow. Now, if you've got that in your head, if you've got one inlet, one outlet, steady state, steady flow in your head, my claim is you can kind of back derive, you can sort of reverse derive something that might be more complex than that. Okay. And so the question is, did you think about using your eyes and your head to simplify the things you need to commit to memory? I totally agree that there is no way you can commit to memory all of the formulas provided in the textbook. So you have to really funnel it down and just get the most critical fundamentals in your head. And so how can you figure out in your own mind with your own style how you keep it simple? So those are my words to the wise, some tricks of the trade to try to help maximize your performance in time-limited situations. Okay, so good luck to everybody as you're preparing to solve thermo problems where you've got to quickly read a problem statement, decide open system or closed system, and then go from there. Okay.